And now, please welcome to the stage one of the Sysdig originals, talking about how to build a chisel, Gianluca Borello.
All right, good morning, folks. Today we are going to talk about two of my favorite topics ever. One of that is writing some code, and the second one is doing real troubleshooting from the fields. It's going to be a lot of fun. So we'll start by talking about extending Sysdig. I decided to talk about this because very frequently in the Sysdig community, online or at conferences, people ask, Sysdig is very cool, but I would like it to do my own thing. I have this very, very custom use case, and I want to make sure that Sysdig can cover it. And we have never given a pretty, let's say, very accurate answer. So I'm trying to address some of those points today. Let me start with a little bit of a deep dive inside the Sysdig architecture. As Luca said, you're already pretty familiar with the concept of the system events that are being extracted by the kernel. And this is a further level of zoom in inside the architecture. So Sysdig is composed by different modules. In particular, we have on top the Sysdig command line interface, or Sysdig, which is the one you have already used in these exercises. This Sysdig command line leverages a couple of very important system libraries that we've wrote that allow to make all the magic happens. And then at the kernel level, we have this little kernel module that fetches all the system calls that happen in the system. So the nice thing about this architecture is that it's indeed modular, and depending on what you're looking to do, you can tap into each of these components to extend Sysdig with your very, very own and custom use case. I'm going to spend 5 minutes in digging down a little bit into all of this, and then we'll have a hands-on part in which we will create a chisel from scratch following a pretty cool use case. So the first part is essentially the command line. Most people should heavily read the Sysdig man page and the Sysdig help section because the command line is absolutely powerful and flexible. It fully embraces the Unix philosophy, so it allows some very great details of customization so that then it can play well with your typical Unix pipeline of commands. So here I have a few examples. For example, as we have seen during this hands-on exercise, by default, Sysdig will print you on screen all the system events, and it will print you the time when they happen, the process name, the event, and then the arguments. But there is much more to it. In some cases where I'm doing some real troubleshooting, depending on what I'm looking for, I'm interested in looking at a very specific subset of fields that I might be interested in. For example, return type of the system call, or number of bytes that have been returned by my read operations because I'm debugging a slow networking issue. So if you use the -p, you're able to customize the output format of Sysdig. And in this case, for example, you can see how I am changing the default output format, and I am getting an output format that contains, for every container, the Kubernetes namespace where this event happened. Which, normally I might not be interested in the specific Kubernetes namespace. But depending on the troubleshooting scenario that I'm digging into, that might be very useful. It's a workflow that is pretty much borrowed from the network world. If you've ever done network troubleshooting with Wireshark, you will know that once you start digging into a troubleshooting use case, you will start filling up all your Wireshark columns by these crazy columns containing the is my TCP specific flag set or not, and you put them as a column because it helps you essentially with the troubleshooting. Then we have other more advanced ways of essentially consuming the Sysdig output. One typical one is the JSON output that will just emit you a stream in JSON of all the events that are going on in the system. So you can use that one, and you can link that JSON output in your super fantastic web application that will show you a chart of how your system calls are slow, for example. And then, as Luca touched just now, I think the greatest ability for Sysdig is its ability to sniff into the I/O of the system. And if you use, for example, the -A, it will print you on screen the I/O buffers as they happen in the system in an ASCII encoding. If you use -X, it will print you the buffers that are being exchanged in the system in a hexadecimal format. And this is nice because then you can copy and paste that to XXD and, for example, reconstruct a binary thing. But don't do that just yet because the use case I have in mind is dangerously close to this one. So again, the command line can be explored absolutely, and it's very powerful. Then we have Chisels. As you have seen at this point, Chisels are really a super, super powerful abstraction that Sysdig exposes, and are really the first-class citizens for extending Sysdig. And again, Chisels are little luascripts, very easy to write, that are automatically discovered by the Sysdig engine, and the Sysdig engine will feed to these luascripts all the events that come from the kernel, along with their full state. So for each event, you can look at the Kubernetes pod or the container where they were generated. And the nice thing about this is that the performance are very good, and you have full access to the whole Lua library, so you can really go crazy with use cases. We have been people from the community really coming up with very, very creative ways to extend Sysdig. And my use case will be pretty focused around that, as we'll see in a couple minutes. Since we are going to dig into the chisels, this is how a chisel essentially looks like. I hope you can see it by looking also at the side monitors. This is a very simple chisel in just a few dozen lines of code that counts how many system calls are being called and filters them by a system call argument that is passed as a parameter. So if you pass it open, this chisel will count you how many open system calls have been called. And the chisel is initialized with a bunch of boilerplate, which is essentially metadata that the user needs to specify in order for the Sysdig engine to discover the chisel. And then the bulk of the action is done by these callbacks. These callbacks are the actual functions that the Sysdig engine will call you, essentially on your behalf, when there is an event ready. For example, you can see in this init section, we are using the Chisel API to ask to the main Sysdig engine to give us these two fields, evt.type and evt.dir, which are just standard filters in Sysdig. And we are essentially telling the Sysdig engine, hey, be ready because I will need those two fields every time you feed me an event. And then we have the core of the chisel. The core of the chisel is by far the onEvent callback. The onEvent callback is the function that gets called every time you get a single event. And in this case, you can see the logic is pretty simple. So we are just getting the event passed as the EVT local variable, and we are comparing the system call name with the one that we got as an argument, and we increment the counter if that's what we needed. And then we have the onCaptureEnd, of course, which is where we print the summary. We print the global counter that we saved. So for most use cases, chisels are by far the stopping line. You should be able to achieve everything you want to achieve in your custom system monitoring to system troubleshooting tool by writing a custom chisel. But if you really want, Sysdig has been designed, again, with modularity in mind, and so it easily can export all the underlying system libraries, and so you can access them. This might be a bit more advanced, so I'm just going to spend a minute on this. But the first library that we expose is libsynsp, that stands for System Inspector. Libsynsp is a C++ library that gets all the events that come from your kernel and builds a very powerful state machine on top of that, a state machine that wants to model the state of your whole operating system. In particular, the state machine contains a table with all the processes in your system. It contains, for every process, it contains the list of files, the list of network connection, the list of containers, the list of cluster orchestrator data. And this state machine is used when in a Sysdig command line or a Sysdig chisel, you specify a filter so that we do the matching between a random event that comes from the kernel and its whole state. So when you see a write on a file descriptor number 5, the system call is in itself stateless if you just analyze it in its singularity. But if you look it up in the state, you can see, oh, this file descriptor 5 is var log whatever.log. using Synsp is a little bit advanced, but is the best way if you really want to build a custom stateful system analyzer. And the interface looks like this. It's a very simple C++ program where you can see you're creating the Synsp object, and then you are opening the object, and then you enter in this while-true loop, essentially, in this event loop, where you're asking the next method to the inspector object, and will fill you a pointer to the next available event. And then, as you can see in the marked red line, once you have the event, you can look back the state of the system attached to that event. You can see that from the event, I'm asking the get thread info, and from the get thread info, I am navigating to the thread object, and then I'm printing the command line of the thread as well as the container ID. So if you start building around this state abstraction, it gets very powerful, as we'll see in 30 seconds now. The next library that you can tap into, and we get even more advanced, is essentially libscap, that stands for lib system capture. Libscap is a much lower level C API that is very similar to libpickup if you've ever done low-level network programming. It's mostly stateless, and its whole purpose is just getting the events from the kernel as fast as possible and feeding them to user space. So it has no state whatsoever. And because of that, it's a very high performance. And it can be used if you want to build advanced system analyzers where you are doing your own housekeeping of the state. For example, a typical use case was the NTOP guys. I'm sure you guys are familiar with NTOP. A couple years ago, they had this very high-performance network packet analyzer. But as Laurie said at the beginning, once you start building a network packet analyzer, it's not easy to see which processes are attached to those packets, to those network packets. And so they were using the driver for capturing their packets, and they were using scap to just get a very thin subset of the system call in order for them to correlate which processes were generating which packets. And then they keep their own state with probably their super efficient hash table or something like that. So that was the perfect use case. Again, this is pretty advanced, so for the typical user, this is not needed. And this is how libscap looks like. So you can notice that there's always an event loop, but the API is now in C. You call the scap open function that returns you a handle. And once you have this handle, you can still get a pointer to the event, but the event doesn't have any state attached to it. So you can pretty much just see the arguments of the system call as if you were in strace. So for most advanced troubleshooting use cases, not very useful. So this completes a very quick overview of the internals of Sysdig, and I hope this answers some of the questions that people had about how Sysdig works. But then let's try with actually get something done, and let's try to really extend Sysdig. Since I'm a very lazy person, I wanted to try to find a use case that I could re-leverage in the community somehow. So I stumbled across this message that came on the Sysdig mailing list a few months ago, where this guy said, all right, I have a Sysdig capture from a server that was compromised. On this server that was compromised, the attacker did a wget to download a binary file. Of course, I don't have access to the server anymore because it has been tainted and whatever, but I still have access to the Sysdig trace file. Is there a way through which I can reconstruct that file? This is really the perfect use case for a custom chisel. Because Sysdig, as you have seen, as Luca just shown you, Sysdig captures all the system calls and all their arguments, so all the I/O content that has been exchanged. So in this trace file, I will see all the activity that wget did to write that file on disk. So if I can just write a chisel that can reconstruct that, I'll be set, and I will have this use case. So the chisel that we're going to write is going to be called the scavenger chisel, because it will essentially parse a Sysdig trace file or even a Sysdig live system, and it will scavenge all the I/O activity captured by Sysdig, trying to actually reconstruct the binary files that we have there. All right, let's jump into, finally, the action. Let's see. I'm trying to 4, 5, 6, 7. This should be probably big enough. If you guys cannot read in the back, also on the side monitor, just raise your hand because it's very important that you can see. So this is the trace file that I have. This is a trace file that I extracted from a very popular blog post that we did a couple years ago. It was called Phishing for Hackers. That was a pretty similar use case. And if you look at this trace file, now I'm reading the trace file with the spy user's chisel, and I can see that the root user did a bunch of terrible things. He created a .tmp directory, it entered in the .tmp directory, and then it downloaded from this very dubious URL this file, rk.tgz. And then it extracted the file, rk.tgz. And of course, with the spy users, I can see what the user actually did, but I cannot see the actual content that was written there. So can we write a chisel to do that? Yes, we can. Let's take a look at how the system events are happening. So without opening the chisel, this is how the trace file looks like. I have a bunch of activity from bash, tar, gzip, wget, really a lot of stuff. And I want to focus on this part, which is the core part. This is where wget opens the file /root /tmp /rk.tgz, and it opens it in create and write only mode. So after the open, I know that the file was opened and written on disk. And now, after wget opens the file, it starts reading a bunch of crap over the network. You can see that it reads from this network connection on port 80. It starts reading this payload. You can see that this pretty much is a binary payload because it's not showing up that well on the standard output. And this crappy payload is just taken verbatim and written in another write operation inside the file, root.tmp rk.tgz. So what if I write a very simple chisel that keeps track of all the opens that are being done and keeps track of all the writes that are being done to a file, and instead of printing the output on screen, it saves it in a local file so that then I can reconstruct what actually happened in my compromised instance? Turns out, yes, I can. So I'm going to split the screen over here. And let's start by writing a chisel. Writing a chisel is really as simple as creating a luascript in your home chisel directory. And here I already put some boilerplate. I already put the description and the name and the category. So now if I do sysdig-cl to list all the chisel, I can go into the IO category, and my scavenger chisel will show up, right? With the description, scavenge everything. Of course, if I run this chisel now on my trace file, it won't show me anything because there is no logic. But turns out the logic is extremely, extremely, extremely simple. So let's actually implement it. A chisel starts with the function onEvent, as we said. That's really the basis of it. So if I just do function onEvent, this will be the whole body of my chisel. So the first thing I can do is, I know that I'm interested in the open events. So how about I get the event type? Create a local variable, eType equal event.getType. And then I filter over here, if eType equal open. Actually, I also need the open at because tar was also doing the open at, as we'll see. Then let's start printing something. Let's build this very calmly and putting a lot of printfs while we iterate. And we can do opening file, end. So if we now run this chisel, we start seeing something slightly more interesting. We start seeing one line of opening file every time a file is open, right? The next thing, right, at some point we need to know the file name because just knowing that a file was open doesn't help us because I need to understand which files were written. So how about I just ask to the Sysdig engine, hey, give me the file name for all those system calls. This is as simple as asking to the Sysdig engine, request field fd.name. Again, I'm asking the name of the file descriptor. And then I'm going to actually use this field for every event. So local name equal evt.field fname. Now I have in the variable name, I have the name of the actual file name. So how about I concatenate this over here, .name. And if I run it again, oops, let me put as a filter just the exit events because I'm just interested. I don't want duplicates. Now I start seeing something interesting. I starting to see all the files that were open. And of course, I also have over here the arcade.tgz. There we are. So we are already doing progress. Now, the next part is, of course, let's intercept the actual I/O activity. So let's intercept the writes. And once again, now you should know how it works. So over here, I can just put otherwise, if the event type was a write, then print write file name. And so now, I not only see the files that are being opened, but also the writes operation. And let's keep iterating over this. We have the file name, we have the writes. Now we need the content, because that's really what we care about, right? The content is super easily available in Sysdig because every write operation has the data field that contains the full binary payload that was extracted by the kernel. So let's ask to the Sysdig engine the data content, fdata, chisel.request field. The data field is under evt.raw argument because I don't want Sysdig to mess up my binary payload with its encoding since I'm going to be stored this verbatim on my system. And then I can ask for local data equal evt.field data, right? And now, once I have the file, I can not only print the file, but I can also print the content data. And if I run this, right. Fdata. Thank you. And if I run this, of course, it will print me a bunch of crap. I'm sure we can also find some nice emoji in these characters. Because that's really not what I need, right? I need to redirect this output on my disk. So how about I start defining a strategy, and maybe I can keep, just this is very basic scripting skills, I can just keep a table in my luascript, a key value sort of table that as a key I put the file name, and as a value I put a string that I append, and I append every time to this string all the content that comes from the write. And then when I see that the file was closed, I just flash all this on disk. This is really, really simple. So let me just do it. So let's create a table over here, files. Creating a map in Lua is super simple. And when we open a file, we just insert files as a key name. We insert an empty string, because of course the file has just been opened. But then, when we actually need to write and we have the data, we just look it up. If file's name exists, because we don't want to save a file that has not been opened during the duration of the trace file, then I can just fetch the content, file's name, and I can put in the same table, file's name, I can put content concatenated with data. Super easy. Let me comment this stuff because we won't need it. And this does really pretty much everything that there was to be done, except that now we need to actually save the file. So to save the file, let's just intercept the close, and let's make sure that whenever we see a close, we serialize whatever in the map we had for that table, for that file name. So over here, else if etype equal close, then let's say if we had the file in memory, then content, file's name, and let's also do if the content len was not empty, because otherwise here we would also intercept all the read activity. Then let's just print scavenging file dot name. And after this, we will start saving the file on disk. So if I run this now, I get a much more interesting output that contains really just the files I was looking for. Scavenging file, with all these, you can see that this is all the files that tar wrote on the disk, because not only I'm intercepting the activity of wget, but also the activity of tar when it extracted the file. So now let's close the loop. And this is really as simple as, instead of printing just scavenging file, let's save it on disk. In Lua, this is super easy. So let me actually do one modification. You can see that here in the files, I have all the slashes. So whereas I want to save them in a flat structure in my local directory. So I'm just going to change the original file name, substituting slashes with underscore. So I can do file name equal string.gsub name slash underscore, just some little boilerplate. And now, again, we keep going on with the boilerplate. So in lieu of writing a file, it's as simple as doing opening a file pointer, io dot output, file name. Then we do io dot write content. And then we do io dot close file pointer. Super easy. Now if I run this, I get the same output of the script. But in my local directory, now I have all the files. All the files that my Chisels scavenged, even if the server was compromised and was long gone. And these are real files. Look, if I do file star, I see the actual file type. So I can see that I have rootkit.tgz. And it's a tar archive that I can actually inspect. But turns out I don't even need to inspect the tar archive because tar, my attacker already decompressed it with tar. So I can just look at the actual thing. And look, I have a bunch of binary LSOF that are actually Linux executable. But let's find, just for the sake of it, something more interesting, something that is Ash readable, right? So for example, this setup script is a bash script. And just to prove you that I was not fooling you, this is really the actual script. We can amuse ourselves into reading it. We can see that this script was written by me, very informative, and is private to do not distribute. It says, do not touch below unless you know what you're doing. Before we move on, let's move on to a safe ground. It even has some rainbow colors. Very nice of the attacker. And it apparently does a bunch of unzipping shits. And I mean, I read this whole script, and this guy, the attacker, should have been a great comedian. Like, the messages he wrote are amazing. Look at this. So patch manually and fuck off. It even contains a typo. So anyway, this is a rootkit, and what it does is a full shell script that does a bunch of health checking, and then it will start replacing all my system binaries inside the system. You can see how it will start replacing TTY load, it will start replacing netstat, it will start replacing PS, it will write a bunch of stuff in my init tab, and there you go. So, and here we have the full file, because if I go down at the very last end, I can actually see the EOF in the script. And I can also see that there's even an email address, so we can maybe get in touch with the attacker, although this was very old because it was 4 years ago. Yeah, so we have been able to reconstruct any file, and this file was in ASCII, but the next one will be, but the other tar file was binary. And so with Sysdig, look at how in just literally 37 lines of very simple code, including also the printf. Let me remove it because I don't like it. So in 35 lines of code, we have been able to achieve this, which is a pretty cool use case. And of course, this is not as thorough as it should be, because I did a bunch of assumptions, because there could have been a snap length for the buffer. So the actual script, if you go on GitHub, it's like double that size. But you will still see how in 10 minutes, we have productively created something that has real value. And in fact, mangling with the I/O has been the biggest use case for people writing their own Chisels. I know of people who have their own binary protocols for their application, and they wrote a Chisel to actually dissect it, because it was easier than doing it than other instrumentation platforms. And this is really the testament on how simple the API is. And as long as you have good data at your fingertips, then you can get all this stuff done. This concludes the talk. In my next one, we will go a bit deeper into advanced troubleshooting use cases. But this was the first part. I hope you liked it.
Gianluca, thanks so much. We're running a little bit late, so we don't have time for questions, but Gianluca is going to be around all day in case you do have some follow-ups for him.